Swayam Prabha. Digital India. Educated India.
Good morning, this is lecture number 29, module 5, matrix analysis of beams and grids. Today we will complete the application of conventional stiffness method and we will introduce the reduced element stiffness method. This is covered in this book which you need to refer to, Advanced Structural Analysis. We will continue with conventional stiffness method. Remember we did different types of problems. We first took a non-prismatic fixed beam, then we did a continuous beam, remember 3-span continuous beam which also had an overhang and we did not take any shortcuts. So we have dealt with different boundary conditions. We also dealt with internal hinges, we also dealt with intermediate supports. Now here is some more types of supports that you can get. You can get the extreme end as being hinged or roller and you can get a guided fixed support. Okay. Now it is possible to take advantage of reduced degree of kinematic indeterminacy and we will do that in the reduced element stiffness method. But in the conventional stiffness method we do not take any shortcuts and actually it is quite easy to deal with any situation. You have to assign the appropriate boundary condition. In the case of a hinged end support, as you see at the end A in this example, we have an active rotational degree of freedom along with a restrained translational deflection degree of freedom. And in support C, guided fixed end support, we have an active translational degree of freedom along with a restrained rotational degree of freedom. And we have done this example earlier, remember it is a symmetric continuous beam, we can take advantage of symmetry, we cut the beam at the middle at C and insert, what kind of support do we insert there? A guided guided roller support as shown here. And let us see how to analyze this. What are the active degrees of freedom? How many of them do we have? Yeah, three active, and the method of analysis is exactly the same. So 1, 2, 3, okay, we start with the left end, rotation at A, rotation at B, deflection at C, these are the 3 active degrees of freedom. Then the restrained degrees of freedom are 4, 5, 6 as indicated there. As far as the local coordinates are concerned, just you have 2 beam elements, each has 4 degrees of freedom, and if you had to write down the in this particular problem, do we have any nodal loads? No, they are all distributed loads. There is no support settlement given also. Now you have to write down the transformation matrix. What does it look like? Can you try the 2 transformation matrices? Well, they are identity matrices, you just have to assign the linking global coordinates. What are the linking global coordinates for number 1? 5, 1,
6, 2.
6, 2, you have to do it in that order. 5, 1, 6, 2 for element 1 and for element 2?
6, 2, 3, 4.
6, 2, 3, 4. You must know the sequence because the translation must match with the translation, do not mix up the rotation. So is this okay? 5, 1, 6, 2, 6, 2, 3, 4, that is all, very easy to do. Next you have to find the fixed end forces. We have done this problem earlier, so I think we can go quite fast. You can work out the fixed end forces. Mind you, we are not taking shortcuts, so you are arresting all degrees of freedom that you identified as active degrees of freedom. For example, in the second case, C is arrested, the rotation at C is arrested, and these are simple fixed end moment calculation that you can do. If you recall, we did this problem by slope deflection and moment distribution method. There we took a shortcut. We took advantage of the fact that there was a guided roller support there, and we modified both the stiffness and the fixed end forces. We do not take those shortcuts in conventional stiffness method. We will take that shortcut in reduced element stiffness method, because this is the normal way computer softwares solve these problems, and we just want to simulate what the standard computer program does. Is it clear? So we really do not care how many degrees of freedom there are, we just want to correctly identify the degree of kinematic indeterminacy. We do not want to take shortcuts of the kind that we did earlier, but if there is symmetry in the structure, definitely it is worth taking dealing with half the frame. So you can work out these are very straightforward. Under a concentrated load, the formula is W minus, not minus, because now it is plus minus, since you are dealing with the conventional stiffness method where anti-clockwise is positive. So it is W A B squared by L squared, you know that formula, you can apply all that and you can get the fixed end force vectors. One more important difference here, you need to get the vertical reactions as well, okay, which is something we did not do when we did slope deflection and moment distribution method. So, and those are easy to compute. In the first case, since it is symmetric, just take the total load 15 into 4 divide by 2, you get the 2 reactions. But when you have an unsymmetric load, you get the shears not only from the load, but you also get from the lack of balance between these two moments. In this case, because this should be both should be anti-clockwise, this should be anti-clockwise, and the difference divided by the span you should add up, okay. Yeah, this should be clockwise, you are right, this should be clockwise, it is an error shown there, okay, but the vectors are correctly shown, and you pre-multiply. Why do we do this exercise? Because we want to find out what the equivalent joint forces are in the structure. So you are pre-multiplying by an identity matrix, but you get along with it the linking coordinates, and then you have done the slotting, you just assemble them properly. You have 6 degrees of freedom, 3 are active, 3 are restrained, and corresponding to 1 you have 20 kilonewton meter, corresponding to 2 you have minus 20 and plus 22.5, which add up to 2.5, and so on and so forth. So this can be easily assembled, is it clear? So this is your fixed end force vector. What do we do next? You find the net, the resultant load vector, which is Fa minus Ff. Fa in this case is 0, it is a null vector because you do not have any nodal loads in this particular problem, and so you can find the resultant force, and you can even draw a sketch to tell you exactly what is happening. This is your resultant force vector, and to remind you once again, the displacements you get at the active degrees of freedom d1, d2 and d3 from this problem, from this nodal load problem, will be exactly equal to the displacements you would have got with the original intermediate loads. Is it clear? That is the equivalence we are trying to establish, okay. It is very effectively done, because you can do matrix analysis only if you are dealing with nodal loads, because the matrix has only vectors which have discrete entities, so your coordinates are limited. Next you generate the element and structure stiffness matrices. Element stiffness matrix is standard, you have 2 elements, all you need is Ei and L. In the first case, actually Ei is constant for both the elements, L is 4 meters for the first element, 2 meters for the second element. So plug in those values, you can get K1 star and K2 star. Clear? Very simple, straightforward. And we have done this problem earlier by moment distribution method. What do we do next? We have to assemble the structure stiffness matrix. To do that, we have to convert from the local axis system to the global axis system through the transformation Ti transpose K star into Ti. Okay. So you do this first, and then you get the same thing again when you pre-multiply by Ti transpose. You have got the linking coordinates, then you have to do the slotting, which I will not explain. Okay. You will finally end up with a full 6 by 6 matrix. The top upper corner is always KAA, the bottom lower corner is KRR, the upper right corner is KAR, the lower right is KRA. You should write a program ideally which will generate this automatically, and you should just take a look and check that it is symmetric and that it's the diagonal elements are all positive, and you're set to handle any loading. Okay, this is what the computer does. The moment you give the geometry of the structure and the material properties, it's ready with the stiffness matrix. Then it's waiting for the loads. You've also got the loads. So now these are your equilibrium equations. If you solve the first equation, you see how familiar this whole thing is now. There's nothing. I mean, once you've got the method, you've got the solution. So solve the first one and you'll get some solution. In this problem, EI was not mentioned. Okay, so if you plug in the value of EI, you will get the answer in millimeters and radians. What do you do next? Find the support reactions. How do you do that? Take the second equilibrium equation and plug in the value of dA. In this problem, dr is a null vector. You will get some answers. And what should you do after you get these answers? No, before that, you must check equilibrium. Okay, you must check equilibrium, and it's a simple check. You can do many checks. You can do a moment equilibrium check, but the least you can do is you just add up the total downward forces must add up to the total upward forces, and it's exact to the third decimal place in your solution. Then you find the member forces. You're familiar with this. Here you have to be careful about one thing. What is that? You've got, okay, there's a Fi star F missing. What's it that you need to be careful about? The Di you have to be careful, because if you go back, you got displacements D1, D2, D3, right? But when you go to the element coordinates, you have 4 degrees of freedom here, right? So you must get the correct Di relevant to the element that you are taking into consideration. For example, the first element, this is the fixed end force vector which you have already got. This is K1 star T1 which you have already calculated and stored in your computer, and now you recognize your linking coordinates are 5, 1, 6, 2, right. So you have to put D5, D1, D6 and D2. Some of them are restrained, for example 5 and 6 are restrained, so they are 0, and you have to pick up D1 and D2 from the solution that you generated from your dA vector. This is the only thing you have to be careful about, and the rest of it follows very easy. Is it clear? You have to select those displacements from your final displacement vector which has dA and dr, which are matching, which are matching your element, and that comes nicely with the linking coordinates which come along with Ki star Ti. You do a similar exercise for the second element, and you get some moments, and then you can draw your free body diagram, bending moment diagram. This is exactly the same solution we got by the methods we did earlier. Is it clear? One last topic before we move on to reduced element stiffness method. Sometimes it becomes necessary to account for shear deformations. When do you think you need to account for shear deformations?
When the member length is very small.
When the span to depth ratio is low. Okay. In normal beams, the span to depth ratio is how much? Well, 10 to 15. If it's above 8 or 7, you won't make any significant error by ignoring shear deformations, and normally well proportioned beams belong to that category. But occasionally, for various reasons, possibly for architectural reasons, you might require a deep beam. So if you've got a deep beam, even if you don't have a deep beam, if you still include shear deformations, you're only going to get a more accurate solution. So the deep beams are those beams in which the span to depth ratio is roughly less than 2.5. Between 2.5 and 6 or 7, you have the middle range, which is between shallow beams and deep beams. Okay. You encounter such situations especially when you deal with shear walls in tall buildings. Okay. So you know, shear walls are the lateral load resisting system, a part of the lateral load resisting system in a multi-story building. The shear wall is essentially a vertical cantilever, but it's connected to different floors through the horizontal framing plan. Okay, you may have beams, you may have slabs, and essentially if it's subject to, and the lateral loads come from those diaphragms at the slab levels in the different stories of a structure. Now if the shear wall is slender, in the sense it's like this, width is small and the story height is large, and there are many stories, then essentially it's going to behave like a flexural element. Okay, the deflection shape will be like that, right? But sometimes you encounter shear walls which are very wide and stocky and the height is less. So when you try to push that shear wall, you will find that the deflection that you get has two components. One is flexural, the other is shear. Remember we did this exercise earlier, shear deflections in cantilever beams, and the shear deflection can be comparable to the flexural deflection. In a cantilever subject to a constant load P at the free end, what is the deflection? PL cube by 3EI, right? But there is also a shear deflection that you get. Remember we did this, which has GA dash coming into the picture in the denominator. So in such instances shear deformations have to come in. Now this kind of beam in which you include shear deformations was originally described in detail by Timoshenko, and sometimes it is referred to as Timoshenko beam. Okay, it is an energy formulation. I am not giving the formulation here, but you can go through it in literature. You will find that you have to modify your element stiffness matrix by including a quantity where you have a ratio of the flexural rigidity to the shear rigidity. Now that is called a shear deformation constant, beta S. So you have EI and you have GA dash I. A dash, G is the shear modulus, which is related to the elastic modulus through the Poisson's ratio, you know that. A dash is not the gross cross sectional area, it is the reduced cross sectional area, to account for the fact that the shear stress distribution is not uniform. Okay, So there is a form factor that comes into play. So this is a non-dimensional factor, that is why L squared also comes in the denominator, and we will see what is a variation of this factor, how it affects the analysis, but and sometimes this formula is useful, okay, and you can easily run this and check what is the error I make if I ignore shear deformations by including shear deformations in any beam problem. This can be also used when you do frame problems. Okay, so all you need to do is to modify this term outside by this factor 1 plus beta s in the denominator, and wherever you had 4 EI by L, you have to add 4 plus beta s into this constant. Where you had 2, you have to put minus beta s. That is all you need to do. So 4 terms in your coefficient matrix get affected, and all terms get affected because this is common outside. Is it clear? So this is a correction you need to do, and check out the solution. Considering a rectangular section and a material with Poisson's ratio nu equal to 0.3, taking on values in the practical range of 0.01 for very high span to depth ratios to 3.12 for L by D equal to 1. Normally you will not get a depth of beam which is less than the span of the beam. Okay, so the variation of 1 divided by 1 plus beta s is between 1 and 0.24 in practice. So that is the kind of range that you get. Obviously when 1 by 1 plus beta s goes to 0.24, it is going to make a big difference, but those are very rare and exceptional cases. We are not going to do any problems, but if tomorrow you need to include it in a real life situation, please make use of this matrix. With this we have covered completely the conventional stiffness method. Now we will look at the reduced element stiffness method. In the conventional stiffness method, we have this stiffness matrix. I am not including shear deformations. What is the rank of this matrix?
2.
Rank is 2. Okay. It is not 3, it is 2. You can easily make out, is it not? Take a look. You can play around with the rows and columns, and 2 of them will, if you find the reduced form. But more easily you can see why is the rank not 4 but 2? What does it point to? There are only 2 equations of equilibrium available. That is why you can't find the inverse of this matrix. It is a singular matrix, but in physically what does it mean when you find the rank is not full? What does it point to?
It depends equations. The other forces
Physically
depend on
what
it.
does it, we have discussed this earlier.
The other forces are
It
dependent.
is unstable, it can have rigid body motion. See, you can have a flexibility matrix only for a stable structure, right, and but you can have a stiffness matrix for an unstable structure. Okay, that is at the element level, not structure. The structure has to be stable, otherwise your structure stiffness matrix will become singular. It is very interesting, your element stiffness matrix is singular, but your structure stiffness matrix will not be singular unless you take the full K matrix. You have KAA will not be singular because you are arresting some degrees of freedom, and you have to arrest a certain minimum number for it to be stable. Is it clear? Now what is the, to make this stable, what should we do? You can arrest any of these 2 degrees of freedom. If you make it simply supported, it is going to be stable. So that is the element we will use. We did this for the axial element, remember, we caught hold of one end and we said you can pull only the other end. Here also you arrest it and you have a simply supported beam. So from now on in the reduced element stiffness method, this is the element that we will use for the element level.
Why can't we use a cantilever?
You can, it's a good question. You can use a cantilever, please do so, but most of us like simply supported conditions, and we are already familiar with 2 star and 4 star. That 4 EI by L, 2 EI by L is now child's play for all of us. So for sheer convenience we have used simply support, but you can also use cantilever. In the book I have discussed this. In the book I have also used a cantilever as an option, but I do not want to confuse you, go by simply supported, okay, but you can also use. Now can you write down the element stiffness matrix for this straight away? It is a 2 by 2 matrix, and we will use the symbol K tilde. What's it?
Some K constant into unit matrix.
Can you extract it from the full 4 by 4 matrix? Can, how do you extract it? What should you remove? What should you remove? What should you remove from that 4 by 4 matrix to just knock off the first column, third column, first row, third row, and whatever you are left with?
442.
So that is the easiest you can do. Whatever you are left with is your reduced element stiffness method, but let us do it in a way that you will appreciate better. Let us use a physical approach and derive the same thing. So what do you normally do to get the first column? You apply D1 star equal to 1, and the moment linked with that is 4 EI by L. You have a carryover moment at the other end which is 2 EI by L. That is all you need to worry about. Do not worry about the reaction. If you want to, the deflected shape will look like that. The point of contraflexure will separate the beam, the ratio 2:1. The bending moment diagram will look like that. Clear? If you now do D2 star equal to 1, you get a similar figure, and from this you can generate your element stiffness matrix. Is it clear? Very easy to and very easy to remember. 4 EI by L, 2 EI by L, 2 EI by L, 4 EI by L, no minus signs here. Clear? Easy. Okay. Now you can also do it from flexibility matrix, because you can, if you invert the flexibility matrix, you get the reduced element stiffness matrix. In the axial element it was very easy because it was 1 by 1, it was EA by L or L by A. Here it is not 1, it is 2 by 2. So let us do this. You remember, if I take the same simply supported beam, apply F1 star equal to 1, the deflected shape will look like this, and if I use conjugate beam method or some such method, I can show that this angle here F1 star 1 star is L by 3 EI, and the angle here will be half this but in an opposite direction, it is minus L by 6 EI, right. And if I do F2 star equal to 1, it look like this. So what is my flexibility matrix? It is going to look like this. Here a negative sign comes, and if I take the inverse of this matrix, I get that matrix. You can work both ways. You can generate the flexibility matrix from the stiffness matrix, or you can, but you can do it only with the reduced element stiffness. Is it clear? Okay. Now let me ask you a simple question. How can you use a 2 degree of freedom element? How can it handle the deflections in your structure? Remember, your global coordinate system has not only rotation, it also has deflections. With this 2 by 2, can you handle it? This is an important question to ask. Is it clear? So how did we manage in slope deflection and moment distribution method? Chord rotation, that is right, we use chord rotation, right. So normally if you do not have chord rotation, your interpretation in this element AB is MAB is F1 star, MBA is F2 star, theta A is D1 star and theta B is D2 star. Okay. These are flexural rotations. Agreed? If you have chord rotation, that means you have relative movement, differential settlement, and now we switch our sign conventions. We say that anti-clockwise chord rotation is positive, vertical deflection upward is positive, not downward. Okay. So dB minus dA both acting upward. If dB is more than dA, you will have an anti-clockwise rotation and phi will be positive. Is it clear? How do you deal with this? What happens in a beam when you have an anti-clockwise chord rotation? You get clockwise end moments. So how can we take advantage of this? Your stiffness matrix does not change. So how do you accommodate? That's right. You have to, you can't touch the left hand side. You play with the D star. You have to somehow accommodate the chord rotation in your displacement vector. How do you do that? So you have to do it in the displacement transformation matrix. So how do you do that?
Theta A minus 3 by
theta A minus phi I. That's what you do. So that's what you do. So it's a clever trick. If you have an anti-clockwise chord rotation, just recognize that the effect it has is that of a clockwise flexural rotation at both the ends. Let us demonstrate this once, because most people who have done this have really not fully understood this. I hope you understand why we are doing it. You can go back to our earlier sessions and see how we did it. So let us say you have some displacement transformation matrix to generate for this element. Let us do it component by component. Let us say from your global coordinate system you have some dj, that dj could be a translation, could be a rotation. Okay, usually they will be upward or anti-clockwise, got it? And you want to write down the effect of that on this 2 degree of freedom element, and there are 4 possibilities. Let us look at them. 2 possibilities are shown here and they are pretty easy. Let us say in your continuous beam structure you had a rotation dj anti-clockwise, it will either go to the left or it will go to the right. So do you agree? If dj corresponds to the left end rotation, obviously d1 star will be 1 times dj and d2 star will be 0. If dj corresponds to the right side of your element anti-clockwise, then it will be 0 1. Is it clear? This is straightforward, there is nothing special about this. The problem comes when you have a deflection. So let us look at that. Let us say you had a deflection in your structure, in your continuous beam. That means your element is going to deflect like this, all other coordinates, all other displacement being arrested. So how will you write d1 star d2 star for this if the length of the element is L? See, I wrote something here, you have to write something similar here for this situation. What will you write here? What is the first component, what is the second component?
0 minus that dj by L.
No, no,
0 minus dj by L, 1 minus dj by L.
no, dj is a deflection.
Dj by L.
Huh? 1 by L is your chord rotation. 1 by L is your chord, because dj is a deflection. You do not put chord rotations in your global coordinates, you put only deflections, get it straight. So you put 1 by L. Now the question is, should you put plus 1 by L or minus 1 by L? So you have to think, if the left end is going up, then you are having a clockwise chord rotation. So you have anti-clockwise end moments. So you should put plus, because anti-clockwise is positive, well done. And the last case is when the right end goes up, that is it. Is it clear? Just to seal your understanding, let us take a look at this situation. I have shown an element here which is part of a continuous beam, okay, and the coordinates are L, M, N, P, it could be anything, and so this is part of a continuous beam, and this could be active degrees of freedom, restrained, I do not care, okay. So let us say they come together like this, dl, dm, dn, dp at the global level. At the element level I have only 1 star and 2 star, right. The element coordinates are d1 star, d2 star, and you need to do this transformation. Can you write down TDI in terms of L, so we are talking of this segment, okay. You will have 4 terms, 1, 2, 3, 4. Tell me what those 4 terms are you getting it? What are those 4 terms?
1 by L, 1, 0, 1 by L.
1 at a time.
1 by L,
1 by L,
1, 0, 1 by L.
okay. This is this portion, okay, this portion. Let us try to figure out. It is very easy. If I lift this up, that is my first coordinate, dl, by unity, do I get a clockwise chord rotation?
Yes.
Do I get clockwise chord rotation?
Yes. Yes, sir.
So I get anti-clockwise end moments which are positive. So the equivalent rotation is positive. Got it? Number 2, if I put dm star equal to 1, what do I get? I get a unit rotation on the left end, so it remains positive, and I do not get anything here, d2 star is 0. Then I have dn star going up by unity. What is my chord rotation? Anti-clockwise. So what are my end moments? Clockwise. Clockwise means it is minus, so minus. And the fourth. Do you get the hang of it? That is it. Because once you got this, we can proceed ahead. You can deal with any problem. But it is only this little bit that you need to understand. The procedure is the same. You have to generate these matrices. The procedure is identical. Okay. Let us demonstrate quickly with one example. This example which we have already done by the conventional stiffness method. Okay. So find out the TD matrix, manually generate the fixed end force vector. Remember we had problems when you had distributed loads in the actual system. Why? Because it can handle only a constant one force, but here you have a distributed loading, so the 2 end moments need not be the same. Okay. We will demonstrate this, and the rest of the procedure is same. Fixed end forces only manually superimpose or generate. So coordinate transformation, if you look at the global coordinates, these are the same coordinates we used in conventional stiffness method. We are not changing here, same coordinates, and local coordinates are what we have just discussed, 2 degrees of freedom. Write down the transformation matrix. Write down the transformation. There are 2 matrices, you have to write TD1 and TD2, you can put it all together also. So let me help you. First of all, the given loading is, you have a nodal moment 30 kilonewton meter. So this is what you will get. Let us do it together. Listen carefully. D1 equal to 1, this goes up. It causes an anti-clockwise chord rotation in element 1 and causes a clockwise chord rotation in element 2. So when you have anti-clockwise chord rotation, you will get clockwise end moments, so you should put a minus sign. So it is minus 1 divided by 10. So you get minus 1 divided by 10 for the left one, and for the right one you get plus 1 divided by 10. Is this clear? You have all got it? I am just extending what we did here. So you fill up the first column for which covers both TD1 and TD2. Second one, D2 equal to 1, you have a rotation here. The right end of this will have 1 and the left end of this will have 1. So 1 1 0 1 1 0. Is it clear? Clear? And now you move to the restraint coordinates. 3 equal to 1. If you lift this up, it affects only element 1. You have a clockwise chord rotation in element 1. So anti-clockwise, that is positive. So you get plus 0.1 plus 0.1, nothing happens to the second element. Number 4, if you give a rotation here, it affects only D1 star 1 in the first element, nothing else happens, 1 0 0 0. Number 5, you lift this up, you have anti-clockwise chord rotation in the second element, clockwise end moments, so equivalent flexural rotation will be negative 0.1 0.1 in the second element, nothing happens. Is this clear? And so on and so forth. Can you do this correctly? You have done. So it is a powerful technique of dealing with deflections, converting them to equivalent flexural rotations through the displacement transformation matrix. We do not touch the stiffness matrix. Okay, so if you have got this step correct, it is easy. Fixed end forces we have done earlier. Okay, so you can find the fixed end forces, find the deflections if you want. We have done this earlier. Put the fixed end force in a vector form. Okay, you have got these diagrams. So this you have to directly get. Okay, in conventional stiffness method you could assemble it doing the contragradient principle, right? You can put Ti transpose. Here you can't do that. Here you have to do it manually. That means you draw these sketches and then you figure out, I want to find out F1. So F1 will be 50 plus 50, 100. Is it clear? I want to find out F2. F2 is this coordinate, that will be 83.33 minus 125, so minus 46. I want to find F3, that is this force, that is plus 50. I want to find F4, that is plus 125 anti-clockwise. I want to find F5, that is plus 50. I want to find F6, that is minus. Is it clear? You have to do it by inspection. No contragradient principle when you are using the reduced element stiffness. But this is okay. In fact, this method is more for manual use. Okay. Yep. That's right. We also do it here, by the way. Here also we write F star. This doesn't change, but we have only 2 here. There we had a 4 by 1 vector. We included 50-50 also, and we did the Ti transpose and we got the linking coordinates and then we did slotting. It was all done mechanically. Here you can't do that. You have to do it with your eyes open. Is it clear? Okay. Then find the net load vector. From now on, it's the same as conventional stiffness method because you've got beyond the element. So this part is common, and of course the element stiffness matrix derivation you have to do carefully. So you have 2 elements. Okay, span is same, EI is changing. Very easy to write down. For 242 4224 EI by L. Then what do you do after you write K star? You do K star TD. TD you've already got. Don't have to write any linking coordinates because you've got all the global coordinates in one go. And then what do? You pre-multiply this with TD star and you just sum up, and you've got the same structure stiffness matrix which you generated in the conventional stiffness method, okay, but you manage with less coordinates. Then this solution is ditto, same as what you did in conventional stiffness method, because you have to invert the Ka, you have to find, so we are just reproducing what we did earlier. What do you do next? Find the support reactions, same equation, okay, you can check equilibrium. Then last step, member forces, you have to do a little carefully. You've done this, you remember when you computed the structure stiffness matrix, you first did Ki star TDI, that comes in handy here because that's what you invoke here, okay, and plug in those values, you will get the same answers. Please go through this problem, solved in the book also, exactly same solution. Is it clear? So we demonstrated one application, we will do all the other applications as well in the next class. Thank you.